In this video, we present our work, RTTF, Rapid Tactile Transfer Framework for Contact-Rich Manipulation Tasks. In robotics research related to dexterous manipulation, optical tactile sensors provide tactile feedback. Currently, the optical tactile sensors used in most studies can be categorized into those based on markers and those based on reflection. We are primarily focused on investigating two key issues: how to achieve policy transfer across different sensors, and how to obtain tactile servo policies for the same sensors. We have studied this issue and made some contributions, and in the following, we will introduce the method we have proposed. To validate the applicability of our method across widely adopted sensors, we conducted experiments using sensors based on different principles. We did not rely on off-the-shelf sensors, aiming to demonstrate the versatility of our approach. Next, we will introduce our method through 4 sections, beginning with data collection. We collected image samples from various types of sensors under different contact conditions. We also gathered a limited set of paired image samples from these sensors under the same contact conditions. Within a certain range of contact angles and contact depths, these paired images include those taken at the same contact angle and the same contact depth. The second part involves a tactile latent space mapping framework. We first used a large amount of unpaired sample data to train a variational autoencoder, obtaining a sparse representation model for each type of sensor. Then, using the paired data, we trained mapping models for different sensors through a supervised generative adversarial network framework. At this point, we have unified the representation models of different sensors into a single simulated tactile sensor representation model through specific mapping models. This process maps the tactile images onto a shared simulated latent space. And by using the decoder, we can reconstruct the mapped simulated images for visualization. Thirdly, using a privileged learning framework, we train both the expert and student policies separately for distinct tasks. The expert policy is trained by reinforcement learning, using observations that include physical parameters that are unattainable in the real world. The student policy, on the other hand, is trained using imitation learning. Its observations are based on the real-world environment and also include historical information. We conducted policy training for several contact-rich manipulation tasks, including robot pushing and surface following. Lastly, the trained student policy can be deployed directly onto the actual system in a zero-shot manner, without requiring any additional adjustments. We first conducted experiments using the reflection-based tactile sensor. In the push task, we examined the performance of our policies under various physical parameter settings, including initial orientation offset, mass offset, and object shapes. The results demonstrated that the policies trained using our approach exhibited notable robustness. We also experimented on markers-based tactile sensors. Even after only replacing the tactile representation model and mapping model, the policy model was still able to accomplish the task. However, due to the limited precision of the sensors, there were instances where significant errors occurred. Replacing the policy model enables task extension on the basis of the representation model and the mapping model. The policy model for the surface follow task was similarly successful in completing the task.